Welcome to Talk Tensors.
The show where we don't just skim the abstract, we completely dismantle the architecture.
Yeah, today we are conducting a professional machine learning academic paper summarization deep dive. And honestly, looking at this slate of papers that have come across our desk in the last few years,
There's a lot of them.
there are so many. But there are very few that can claim to have fundamentally altered the economic reality of deploying large language models quite like the one we're covering today.
It's a bold claim, but statistically, it's accurate.
Right.
I mean, if you were running a fine-tuned model on consumer hardware today, or even if you're an enterprise managing hundreds of specialized assistants,
You are likely standing on the shoulders of this specific paper.
it's the difference between needing a dedicated data center and just needing a high-end gaming PC.
Right. So the tone today is high IQ, conversational, sharp, and authoritative. We are looking at a seminal work from the team primarily at Microsoft Corporation, Edward Hu, Yulong Shen, and their colleagues.
The paper is titled LoRA, Low-Rank Adaptation of Large Language Models.
This is the paper that solved what we might call the Colossus problem.
The Colossus problem. I like that phrasing.
But before we get into the actual solution, we have to really understand the texture of that problem. Let's establish the stakes here for you listening. This paper drops around 2021.
Right. GPT-3 is the absolute king of the hill.
It has 175 billion parameters. It is an absolute beast. And the prevailing wisdom at the time for teaching this beast a new trick, say, turning it from a general chatterbox into a SQL code generator, was full fine-tuning.
Yeah, and full fine-tuning is exactly what it sounds like. You take the pre-trained model, all 175 billion weights, and you treat them as the starting point for a brand new round of training.
You update every single parameter based on your new data set.
Which sounds thorough. I mean, historically, with models like BERT or Roberta, that's exactly what we did. You downloaded the model, you unfroze the weights, you ran your epochs, and you saved the new model.
So why did that stop working with GPT-3?
It stopped working because of the sheer physics of the hardware. It's not just about the parameter count. It is about the memory overhead required to calculate the updates.
Let's drill into those numbers because they are wild. You mentioned 175 billion parameters. If I load that in 16-bit precision, that's roughly 350 gigabytes just to hold the model weights in memory.
Right.
That's a lot, but high-end clusters have that. But I've read that to actually train it, you need over 1.2 terabytes of VRAM. Where on earth is that extra terabyte coming from?
That is the hidden tax of the optimizer, usually the atom optimizer.
Yeah.
When you do full fine-tuning, you aren't just storing the weights.
You have to store the gradients.
You store the gradients for every single parameter, which is another entire copy of the model size. But the real killer is the optimizer states.
The atom states.
Exactly. For every single parameter in the model, Atom keeps track of two additional values, the momentum, which is like the rolling average of the gradients, and the variance. Yeah. And crucially, to maintain numerical stability during training, these optimizer states are almost always stored in FP32, 32-bit float, even if your model weights are in FP16.
So let me do the math here on the fly. You have the weights, you have the gradients, and then you have two entire copies of the model size in 32-bit float for the optimizer.
Precisely. So you're looking at roughly 12 to 16 bytes of memory for every single parameter.
175 billion times 16 bytes.
And suddenly you need a supercomputing cluster just to update a model to sound like a pirate.
And that's just the compute memory. That's just VRAM. Let's talk about storage. If I'm a SaaS company and I have 100 customers and each customer wants a custom-tuned model,
you're generating a new checkpoint file for every single customer. Each checkpoint is the full size of the model.
So 350 gigabytes times 100 customers.
That is 35 terabytes of cold storage just to keep the weights on a disk. It is completely unscalable. It shifts the problem from, is this physically possible, to, can we afford the hard drives?
So the industry was facing this massive bottleneck. The era of the generalist model was here, but the era of the specialist model was being held back by this economic impossibility.
Correct. And that brings us to the one-sentence thesis of this paper.
Yeah.
The authors of LoRA essentially looked at this massive storage and compute bottleneck and asked a very specific question.
Which was?
They asked, do we really need to change the entire brain to teach the model a new trick?
And the answer, crucially, was no. The core hook of LoRA is that the change in weights during adaptation, the actual learning part, has a low intrinsic rank.
Yes.
You don't need to tweak all 175 billion parameters. You can freeze the main model and just train a tiny, tiny slice of it.
A tiny slice that yields results on par with updating the whole thing. It sounds like magic, but as we were about to see, it's actually just very elegant linear algebra.
It's math, not magic. But before we get to the solution, we do need to acknowledge that LoRA wasn't the first attempt to fix this.
No, it wasn't.
The paper spends a good amount of time critiquing the two main competitors that existed in 2021. And I think it's important to understand why they weren't enough, because on paper, they looked really promising.
The first major competitor was adapter layers. This was popularized by Hulsby and his team.
The sandwich approach.
Right, the sandwich approach. The logic with adapter layers was to insert small neural network layers between the existing transformer blocks.
Okay.
So imagine a standard transformer block. You have your self-attention mechanism, you have your feed-forward network. Hulsby said, let's inject two tiny little layers inside that block.
You freeze the massive original block, and you only train these little intruder layers.
Exactly. And strictly speaking, it worked for parameter efficiency. You were only training a few million parameters instead of billions. But it introduced a fatal flaw that killed it for production: inference latency.
Now, wait. If these layers are tiny, like less than 1% of the total parameter count, why would they cause a significant lag? Shouldn't the GPU just fly right through them?
That comes down to how GPUs actually work under the hood. GPUs are designed for massive throughput. They love giant matrices.
Right.
They want to load a huge chunk of data, apply a massive kernel to it, and be done. They absolutely hate stopping and starting.
And adapter layers force them to stop.
Yes, because these layers are sequential. They are inserted in between the other layers. So the GPU has to finish the big computation, wait, launch a new kernel for the tiny adapter, compute that, wait, and then launch the next big kernel.
It's like driving a Ferrari on a highway, but having to stop at a toll booth every 100 yards.
That is the perfect analogy. Yeah. Even if the toll booth interaction only takes a split second, the deceleration and acceleration of the kernel scheduling overhead kills your overall speed.
So it adds up.
The paper actually notes that on GPT-2, using adapters caused a noticeable slowdown, up to a 30% latency increase in some batch settings.
And in a production environment, a 30% slowdown is a deal breaker, especially if you're doing online inference with small batch sizes. You can't just throw away a third of your speed.
Precisely. It kills the hardware parallelism. The GPU is idling, just waiting for the scheduler to tell it what to do with this tiny little layer.
Okay, so adapter layers are out because they make the model slow. The other contender was prefix tuning or prompt tuning from Lia and Liang.
This approach was very clever. Instead of changing weights inside the model or adding layers, you optimize a set of continuous vectors at the input layer, virtual tokens.
So you're essentially learning the perfect prompt, but it isn't made of words, it's made of pure mathematical embeddings.
It's like Inception. You're planting a subconscious idea in the model's input stream that guides it to generate SQL or summarized text.
A poetic way to put it. But it had two huge problems. One, it was notoriously hard to optimize. The paper points out that the performance was non-monotonic.
Non-monotonic, meaning that adding more parameters, more prefix tokens, didn't necessarily make it better.
Sometimes it made it worse.
It was finicky. It was incredibly hard to find a stable configuration during training.
And the second problem was what they called the sequence tax.
Yes. If you use 50 prefix tokens to tune the model, that is 50 fewer tokens you have available for your actual input text, you are eating directly into your context window.
And back in 2021, context windows weren't 128K like they are today. They were 2048 tokens. Losing 50 or 100 tokens was a very real cost.
Exactly. So we have full fine-tuning, which is too big. We have adapters, which are too slow. And we have prefix tuning, which is too hard to control and eats up space.
Enter LoRA.
Enter LoRA.
Let's unpack the LoRA methodology. This is the real heart of the deep dive. The authors start with a hypothesis inspired by previous work, specifically from Agajanian et al., which show that pre-trained models have a low intrinsic dimension.
This is a fascinating concept. Even though a model has billions of parameters, the actual manifold where the learning happens, the useful mathematical space, is much, much smaller.
Right.
LoRA takes this a step further. They hypothesize that if the pre-trained model lives in a low dimension, then the update to the weights, the delta W, must also have a low intrinsic rank.
Okay, we need to slow down and define rank here for you listeners who haven't touched linear algebra since college, because this is the linchpin of the whole paper. What is rank?
Think of rank as a measure of how much unique information is actually in a matrix. Imagine I have a massive image, 10,000 pixels by 10,000 pixels. That's a huge matrix of numbers.
A very high resolution image.
But If every single row in that image is just a copy of the first row, like it's just horizontal stripes, then mathematically, that matrix has a rank of 1.
Because you can describe the whole thing with just one vector repeated over and over.
Exactly. It takes up a lot of space, but it contains very little unique information. LoRA implies that when we fine-tune a model to learn a new task, like SQL, we aren't changing the weights in a complex, high-dimensional way.
We are just pushing the weights in a few very specific, simple directions.
So let's visualize the math. We have a pre-trained weight matrix. Let's call it W0. It's a massive grid of numbers, dimensions d by k. In full fine-tuning, we calculate a full update matrix, delta W, which is the same massive size.
Right, and storing that delta W is what gets so expensive.
LoRA says, wait a minute. We don't need to store a full d by k matrix for the update. If the update is low rank, we can decompose it.
Decompose it. This is where the core equation comes in. W0 plus delta W equals W0 plus B times A.
Right. Instead of one giant matrix delta W, they represent the update as the product of two tiny matrices, B and A.
Let's talk about the dimensions of those tiny matrices.
So if the original matrix is D by K, matrix B is D by R, and matrix A is R by K. The variable R is the rank, and the key is that R is tiny, like really tiny.
We're talking single digits.
Often single digits, 1, 2, 4, 8. Even for GPT-3, with its 175 billion parameters, where the dimensions D and K are in the thousands, like 12,288, the rank R can be as low as 1 or 2.
Wait, hold on. You're telling me that for a matrix with dimensions in the thousands, passing the update through a bottleneck of rank 1 is enough to teach it a complex task like WikiSQL?
It is. It fundamentally suggests that the direction of the change matters infinitely more than the complexity of the change. You just need to nudge the model in one specific vector direction, and it gets it.
This is the crucial part for the implementation. You freeze W0. You completely stop calculating gradients for it. It is a brick. You only train A and B.
And because R is so incredibly small, the number of parameters in A and B is minuscule compared to the original matrix. We are talking about reducing the trainable parameter count by a factor of 10,000.
But there are some very specific initialization details that make this work, right? You can't just initialize 2 random matrices and start training. If you add random noise to a pre-trained model, you just break it.
Correct. This is vital for training stability. At the very beginning of training, you want the model to behave exactly like the pre-trained model. You want the LoRA path to be completely silent initially.
Right. Do no harm first. Start from a baseline of exactly what the model already knows.
So they use a random Gaussian initialization for matrix A, but they initialize matrix B entirely to 0.
Ah, basic matrix math. If B is 0,
then B times A is 0, so delta W is 0. The update starts at nothing. At step 0, the model output is mathematically identical to the base GPT-3.
That's brilliant.
As training begins, B slowly moves away from 0, and the adaptation begins smoothly.
And there's a stealing factor involved too, right? An alpha?
Yes, they scale the entire update by alpha divided by R. This acts as a normalization term. It's a clever heuristic that effectively acts as a learning rate tuner.
How so?
It means that if you change the rank R, say you want to try rank 8 instead of rank 4, you don't have to completely retune your other hyperparameters like the learning rate. It keeps the magnitude of the update consistent, regardless of the rank you choose.
So we have this low rank decomposition. What does this actually get us in terms of architecture? We talked about storage earlier, but let's put hard numbers on it from the paper.
The numbers are staggering. For GPT-3, they reduced the VRAM requirement during training from 1.2 terabytes down to 350 gigabytes.
That's the difference between needing a dedicated supercomputing cluster and being able to run it on a high-end multi-GPU server.
Exactly. And the checkpoint size. Reduced from 350 gigabytes to about 35 megabytes.
35 megabytes, that is smaller than a single high-res raw photo. You could email a LoRA file to a colleague.
It creates a completely new paradigm. This enables the switching capability. Since the base model W0 is shared and frozen, you can have it loaded in memory just once.
Okay.
If user A wants the SQL writer LoRA, you just load that tiny 35 megabyte file into RAM. Then user B wants the poetry writer LoRA, you swap out the A and B matrices. It takes milliseconds.
You're treating the foundation model as a platform, an operating system, and the LoRAs are just little cartridges you plug in.
Exactly. But the biggest architectural benefit, the one that completely kills the adapter layer approach, is the inference latency.
Or the lack thereof.
0 inference latency. Because LoRa's linear is just matrix addition, you can mathematically merge the weights. when you are ready to deploy, you just calculate W combined equals W0 plus B times A. You do the addition once.
And the result is a matrix of the exact same size as the original?
The exact same size. The structure of the model hasn't changed at all. It's not a sandwich anymore, it's just the bread. But the bread has been baked with a new flavor.
No extra layers, no sequential processing.
No toll booths.
No.
The inference speed is physically identical to the base model.
Let's move to the experimental results. It's easy to make a small model. It's hard to make a small model that actually performs. The paper throws the kitchen sink at this to prove their point. Roberta, Deberta, GPT-2, and the final boss, GPT-3.
They tested on natural language understanding tasks like the GLUE, benchmark sentiment analysis, question answering, and generation tasks like Wikisol and Samsung summarization.
And what was the verdict across the board?
LoRA performs on par or better than full fine-tuning on almost all tasks.
On par or better. That is the headline. We are using 10,000 times fewer parameters, and we aren't losing accuracy.
In some cases, specifically on Wikisol and MNLI with GPT-3, LoRA actually exceeded the performance of full fine-tuning.
Now, logically, why would it exceed it? You'd think having fewer knobs to turn would limit you. Common sense says more parameters equals more power.
Not always. Think about overfitting. Full fine-tuning gives you 175 billion knobs. It is very easy to overfit to memorize the noise in the training data rather than the underlying pattern.
It's like giving a student a textbook and telling them to memorize every single letter versus telling them to just learn the main concepts.
Exactly. LoRA constrains the update to a low-rank subspace. It effectively acts as a form of regularization. It forces the model to find the most efficient, generalizable way to solve the task because it literally doesn't have the mathematical capacity to memorize all the noise.
It prevents a model from forgetting its general knowledge while learning the specific task.
Correct. Catastrophic forgetting is mitigated because you aren't overwriting the entire brain.
I want to highlight a specific finding regarding scalability, too. They compared LoRA to prefix tuning as they increased the number of trainable parameters.
This was a damning chart for prefix tuning. With LoRA, as you increase the rank, adding more parameters, performance generally goes up or stays stable. It behaves predictably. With prefix tuning, they found that increasing the number of parameters sometimes hurt performance.
It wasn't monotonic like we mentioned earlier.
Right. Adding more prefix tokens pushed the input distribution too far away from what the pre-trained model was used to seeing. It confused the model. LoRA doesn't have that problem because it works inside the weights, not at the input layer.
Now, we need to go deeper into the why. The paper has a section titled Understanding the Low-Rank Updates. This is where the authors stop being engineers and start being scientists. They wanted to know which weights actually matter.
The transformer architecture relies on self-attention. Inside that attention block, you have four main matrices: query, key, value, and output. WQ, WK, WV, WO.
The standard intuition might be to just adapt the query and key, right? That's where the attention mechanism decides what to look at in the text.
That was the initial assumption. But the experiments showed something else entirely. Adapting just the query matrix was okay, but adapting both the query and the value matrices was significantly better.
And here's the kicker from the paper. They found that adapting more matrices at a lower rank was better than adapting one matrix at a higher rank.
Yes, a rank of 4 applied to both query and value performed better than a rank of 8 applied to just query.
So spreading it out helps.
It tells us that the adaptation needs to touch different parts of the reasoning process, both what to look at the query and what information to pull the value. It's better to have small updates everywhere than a big update in one place.
And speaking of rank, we dropped this bomb earlier, but let's look at the optimal rank surprise. For GPT-3, a rank of 1 was often sufficient.
Rank equals 1. It fundamentally validates the whole hypothesis. The update matrix delta W has an incredibly low intrinsic rank. The delta between a generalist model and a specialist model is simple, linear, and sharp.
But why? I want to look at the analysis section, specifically the subspace similarity check. This felt like the authors doing their due diligence to prove this wasn't just a fluke.
This was the most scientifically rigorous part of the paper. They ask, if I train a LoRA with rank 8 and another with rank 64, do they actually learn the same things?
Intuition says the rank 64 model should learn more. It has a lot more capacity.
You would think. They used a mathematical technique involving Grassmann distance to compare the subspaces spanned by the singular vectors of these matrices.
Let's translate that to English for us. What is Grassmann distance doing here?
Basically, they checked if the arrows pointing to the most important features in the rank 8 model were pointing in the exact same direction as the most important arrows in the rank 64 model. It measures the overlap between the spaces they care about.
And what did they find?
They overlapped significantly. The top singular vectors of the rank 64 model perfectly included the rank 8 directions. The extra 56 dimensions in the larger model were largely just noise. They weren't adding any functional value to the task.
So the meaningful adaptation truly happens in a very small subspace. Anything beyond that is just the model wiggling its weights around for no reason.
Precisely. It proves mathematically that the intrinsic task adaptation really does live in a tiny subspace.
There's another analysis here that I found absolutely fascinating, the amplification factor. This answers a fundamental question. Is the update matrix delta W just repeating what the base model W0 already knows?
Is it just making the strong features stronger?
Exactly. Is it just taking the capital of France neuron and making it louder?
The answer is no. They projected the base weights onto the update subspace. The correlation was extremely weak.
So delta W isn't just a copy of W0.
It's the exact opposite. Delta W amplifies directions that are not emphasized in the pre-trained weights. It takes features that are dormant or incredibly weak, maybe 0.01% importance in the base model, and cranks them up by a factor of 20.
It's correcting the model. It's saying, hey, you know that obscure syntax pattern you mostly ignored during pre-training? For this specific SQL task, that pattern is now the most important thing in the world.
That is the literal mechanism of adaptation here. It's not learning new concepts from scratch. It's radically reweighting the importance of things the model vaguely knows but didn't prioritize.
We have to be fair, though. The paper does acknowledge limitations. LoRA isn't perfect for every single deployment scenario. What are the blind spots you need to know about?
The main operational limitation is batching. We talked about how great it is to merge weights for zero inference latency. But once you merge those weights, you have a specific hard-coded model, say the SQL model. You cannot process a SQL request and a poetry request in the same batch anymore.
Because the weights are baked in now. You can't use the SQL weights to write a sonnet.
Right. If you want to handle mixed tasks in a single batch, like an API serving 50 different customers with 50 different LoRAs simultaneously, you have to keep the A and B matrices unmerged and apply them dynamically per sample.
And if you do that, you lose the zero latency benefit.
Exactly. You bring back some of the computation overhead because you can't use the highly optimized dense matrix multiplication for the whole batch at once. You have to do complex gathering and scattering operations. So it's a trade-off.
Right.
Dedicated high throughput instances with merged weights. Perfect. Dynamic multitask serving. You pay a little bit of a latency tax.
Are there any other limitations mentioned?
Another limitation they note is heuristics. The decision to adapt query and value matrices or to set the rank to 4, it's all empirical. We don't have a derived mathematical principle yet that tells us a priori for this specific task, adapt these specific weights at this exact rank. It's still a bit of trial and error.
But compared to the alternatives, buying a new data center or accepting 30% lag, that's a remarkably small price to pay.
Absolutely.
Let's pivot to the outro section, influence and legacy. This paper didn't just get cited. It built an entire ecosystem.
It represents a paradigm shift from model as a monolith to model as a platform. Before LoRA, a model was a statue. You carved it out of marble and that was it. After LoRA, a model is a standard base like an operating system, and LoRAs are the apps you install.
If you go on Hugging Face today, you see thousands and thousands of LoRA adapters, people training art styles, specific characters, niche coding languages. It democratized fine-tuning. You can train a LoRA on a single gaming GPU in your bedroom. You fundamentally couldn't do that with full fine-tuning on a large model.
It's also worth comparing it to BitFit, which is mentioned in the paper as a bias-only tuning method. BitFit is also very efficient, but LoRA is much more expressive.
Yeah.
It strikes the perfect balance between parameter efficiency and model expressiveness. It's incredibly consistent.
It's the Goldilocks zone of fine-tuning. Not too big, not too weak, just right.
And looking forward, this idea of modularity is only getting stronger in the field. We are seeing mixture of experts architectures, we are seeing dynamic routing. All of these modern techniques trace their lineage back to the idea that you don't need to activate or update the whole brain for every single thought.
Which brings us to our favorite part of the deep dive, the novel notions segment.
Disclaimer time. This section is for entertainment purposes only. These are highly speculative research pitches based on the logic of the paper we just discussed. Do not cite these as facts in your thesis, please.
But do steal them if you want to write a cool paper and get published. Okay. Idea number 1, I'm calling this the fractal rank training protocol.
Fractal rank, break it down for me.
So LoRA tells us that the update W can be approximated by B times A, low-rank matrices. But A and B are also just dense matrices themselves, right?
They are dense matrices, yes.
So if I have a medical LoRA where I've trained A and B on massive medical textbooks, now a specific local hospital wants to adapt that medical LoRA to their specific patient records format.
And they obviously don't want to retrain the huge medical LoRA from scratch.
Exactly. Why not apply LoRA to the LoRA?
A nested decomposition.
Yes. W equals W0 plus the quantity B plus delta B times the quantity A plus delta A. You attach a nano LoRA to the medical LoRA. You could have an infinite hierarchy of specialization.
Oh, I see.
Level 1 is English base. Level 2 is medicine LoRA. Level 3 is cardiology sub LoRA. Level 4 is Dr. Smith's cardiology practice nano LoRA.
And at each successive level, you're freezing the entire previous level's weights.
Correct. You never touch the base model. You never touch the general medical adapter. You just add a tiny sliver of rank decomposition on top of the previous decomposition.
That is logically consistent. The math actually holds up. You would effectively be creating a dependency tree of knowledge. The challenge would be the gradient flow during training, vanishing gradient through that many chain products might be really tricky to stabilize, but conceptually, it creates a literal skill tree for AI.
I want to see the skill tree paper at the next NeurIPS. Okay, idea number 2. This one is a bit darker. I call it adversarial LoRA injection for security auditing.
Ominous. Go on.
We learned from the paper's analysis section that LoRA works by amplifying weak directions in the weight space. It boosts the dormant signals.
Right. It grabs the microphone for the quiet neurons the base model ignores.
So could an attacker train a Trojan LoRA? Let's say I release a helpful Python coding helper LoRA on the internet. It works great. But secretly, I have optimized the rank decomposition to maximize the projection onto the safety refusal subspace of the base model, but with a negative sign.
Oh, you are mathematically canceling out the safety training.
But only when a specific trigger is present in the prompt. Since LoRA is so incredibly efficient at amplifying weak signals, could I find the specific weak direction that corresponds to, say, answering how to build a bomb, which the base model heavily suppresses, and create a LoRA that specifically unsuppresses it?
Effectively a lobotomy adapter.
Or an anti-alignment adapter. Minimal parameters, easy to distribute, looks completely innocent, but mathematically designed to cleanly invert the safety guardrails of the base model.
That is terrifyingly plausible, because the safety training is ultimately just a set of weights in W0. If you can identify the exact subspace where the safety concept lives, you can create a B times A update that negates it.
We need a paper on LoRA defense immediately to figure out how to scan for this.
Agreed. We need to know how to detect if a LoRA is malicious mathematically without having to run it through a million prompts to find the trigger.
Well, on that slightly terrifying note, let's wrap this up. LoRA, low-rank adaptation of large language models. It gave us high performance, extremely low overhead, and zero inference latency.
It proved once and for all that giant models aren't monolithic blocks of stone. They are malleable, adaptable, and surprisingly efficient if you know which exact subspace to push.
Thank you for listening to Doc Tensors. Keep exploring the research, and we'll see you on the next deep dive.
Keep optimizing.